Hey class, this is Juan Ramirez with EE2715, Linear Circuits 2, Transients. Today we're going to cover how to analyze a circuit using Laplace transforms. So last time we looked at how we can essentially represent different circuit elements in the S domain. We looked at how we represent a voltage source, a current source, but same goes for a resistor, inductor, or capacitor. We also said that for the resistor, inductor, capacitor, instead of looking at them as such, we represent all three of them with what we call an impedance, where the impedance is the ratio of voltage to current in the S domain. Ended up determining that the impedance of a resistor is the resistance, the impedance of an inductor is S times the inductance, and the impedance of a capacitor is 1 over S times the capacitance. Now we're going to actually analyze these circuits in the S domain and then convert them back into the time domain. And we'll see that essentially the analysis becomes a lot easier for transient circuits. So the main thing to know is that all of the circuit theorems and relationships that we developed or covered for DC circuits are valid. They're valid in the S domain. Today we'll cover a couple of examples to kind of illustrate this, but essentially Ohm's law, voltage division, current division. If we look at the way we combine impedances instead of resistances, we look at them as impedances, so a combination of parallel and series impedances, and then nodal and mesh analysis, and then source transformations. All that essentially gets applied the same way in the S domain as it does in the time domain. So let's do a couple of examples. Okay, so for this series RLC circuit, we want to find the current in the time domain. We learned a step-by-step method on how to do this, but we also kind of realized that that step-by-step method takes quite a bit of time to do. Let's see how long it takes us to analyze this series RLC circuit with a step input by just using the Laplace domain analysis. So the first thing we do is we convert this circuit from the time domain to the Laplace domain. So we'll redraw the circuit. So then we take the Laplace transform of that voltage source, 8u of t. So the Laplace transform of a step function is 1 over s. So we multiplied that by 8 because of the coefficient it has. So it's 8 over S. Resistors, remember the impedance in the S domain of a resistor is just the resistance. An inductor is S times the inductance, so S times 1. And the impedance of a capacitance is 1 over S times the capacitance. That's 1 over S. And we are looking for now S domain current. Okay. So over on the right, I'm just going to make a couple notes. Ohm's law, which was one of the very fundamental laws that we use to analyze circuits, it applies in the S domain the same way. So in the time domain, for some equivalent resistance, the voltage across that equivalent resistance is equal to the current through that equivalent resistance. Okay, well, in the S domain, it looks the same. Instead of resistance, we say impedance. But the equation is pretty much the same. So, what's our equivalent impedance in this case? In this case, our equivalent impedance is equal to 1 plus S plus 1 over S, because that resistor, inductor, and capacitor are in series, so their impedances will add up like resistors do in series. You may say, oh, but it's one of them is a capacitor. Capacitors in series get combined differently. That's true. But it's not true for impedances. It's true if we're putting together capacitors with their capacitance values. Once you look at impedances, you've sort of neglected that way of combining capacitances. So impedances combine just like resistors do. Okay, so now we are looking for I of S. That's equal to the voltage across that equivalent impedance, according to Ohm's law. Because that voltage source, that same voltage gets dropped across that equivalent impedance. That voltage is equal to 8 over S. The equivalent impedance is 1 plus S plus 1 over S. I don't like having that 1 over S in the denominator, so I'm going to multiply top and bottom by S. And we end up with S squared plus S plus 1. And now this just becomes, again, one of those cases where we'll try to convert that back to the time domain by doing the inverse Laplace transform. Notice that the denominator has a degree of 2, but I can't factor it out, right? However, there is a Laplace transform pair that I could find that kind of looks like this, a little bit. Let's see, I'm going to whip out my table. So according to my table, I'm going to do this in a different color. A time domain function e to the negative at times sine omega t has a Laplace transform of omega s plus a squared plus omega squared. So then the question becomes, can I put this I function to be in that same form? And the answer is yes. So how could I get my s squared plus s plus 1 to look like s plus a squared? And the way we do that is we have to write it as s squared plus, we only have a value s, so the constant will have to be 0.5, so that when you multiply by it twice, you end up with 0.5 plus 0.5. This guy right here is equal to s plus 0.5 squared. Well, that's fine, but what about, we had a constant of 1, here we only have the 0.5, so out here, you have to add the 0.5 as well. That way, these two denominators are still equal. Okay? So now I can rewrite this. 8 over s plus 0.5 squared plus 0.5. As soon as I do that, I could tell, hey, my value of a is equal to 0.5. My value of omega squared is equal to 0.5. Therefore, omega is the square root of that. Square root of 0.5 is 0.707. So notice we have to be kind of clever with how we're doing this. Nothing too complex, but just have to be aware. Alright, well, the numerator, if I want to use that Laplace transform pair on the left, the numerator has to be equal to omega. So I have to do something so that I'm going to rewrite over here, I of s is equal to 8 times omega. So let's say instead of 8, I'm just going to put omega here, 0.707. And then I'm going to put 8 divided by 0.707. That ensures that this function is now in the form omega over s plus a squared plus omega squared. What is 8 divided by 0.707? It's about 11.3. Okay, now it's really in the form that we wanted. And now we can find our I of t by doing the inverse Laplace transform on this whole thing. And you end up with, as long as, or because of the way we set it up, a is equal to 0.5, omega is equal to 0.707, you end up with 11.3 e to the negative a, which is 0.5 t, times sine, which is 0.707, times t. That's our answer. And that's in amps. Alright. So that one was a tricky one, mainly because getting it back into the time domain, performing that inverse Laplace transform took some manipulations of the variables. But the actual circuit analysis was straightforward. It was using the same theorems and relationships that we've used in the past for DC circuits. Let's do one more example. Alright, so let's look at the circuit that we'll draw below and use Laplace analysis to find the output voltage. We're going to assume the input current is equal to e to the negative t u of t in amps. Alright, and the circuit looks like this. Okay. So again, first step is to redraw the circuit in the S domain. So what is the Laplace transform of the current source value? E to the negative t. So we'll pull out our Laplace transform table, and we see that e to the negative at is 1 over s plus a. In this case, a is 1, so it'll be 1 over s plus 1. How about the resistance 2? The S domain impedance will be the same as the resistance 2. Same goes for the resistance 1 of value 1. And then for the inductance of value 1 Henry, the impedance will be S times 1 Henry. And what we're looking for is the S domain output voltage. Okay. Now, to find that output voltage, you can do a couple different things. One thing you can do is current division. So that's one way to go about it. In fact, probably one of the easier ways. But then there's another way you can do it. You can do it with source transformations, which is a slightly less intuitive way. So how about let me go ahead and do both. Current division, I'll just kind of start off. And say the current through that inductor will be equal to the current source value times the impedance of the opposite impedance all over the sum of both the impedances. Okay, so that'll give you 2 over s plus 1 times s plus 3. And then the output voltage will be equal to that current times that impedance. If we remember Ohm's law in the S domain, voltage is equal to current times impedance. So that current will be equal to 2 over, here I'll just write out that equation real quick. Here the equivalent impedance is just S because we're looking at the voltage across the impedance of the inductor, only the inductor. Alright, so you end up with that. That's your output voltage in the S domain. And then you do the inverse Laplace transform. First you'll have to decompose the fraction, partial fraction. You decompose it, you then end up with your output voltage in the time domain. That's one way. Let me do a slightly more complicated way, just to also show that we can do source transformations and voltage division and whatnot. Okay, so if you remember, in source transformations, you have a Thevenin voltage and Thevenin resistance, or you could have a Norton current and Norton resistance. And you could go from one to the other using the following relationships. Well, it turns out we can do the same exact thing with impedances and in the S domain. Can we notice that the current source in green, in that little green bracket, the current source and the 2 ohm resistor make up a Norton equivalent circuit. That means I can convert it into a voltage source and a series resistance, or a Thevenin resistance. In this case, we'll call it impedance because we're in the S domain. So actually, let's go ahead and do that. What would the voltage be equal to? It would be equal to the Norton current, which is 1 over S plus 1, times the Norton impedance, which is 2. And the Thevenin impedance will be equal to the Norton impedance, which is 2. And then you keep the rest of the circuit, which was what we would consider the load. Now what we can do is voltage division, because you know the voltage across that series string of impedances, and you're looking for the voltage across one of the individual impedances. Voltage division will be equal to V out, equal to the input, which is 2 over S plus 1, times the impedance that you're looking at, which is S. Again, impedance is sort of the analog to resistance. An impedance could be a resistor or an inductor or a capacitor. So S goes in the numerator, and then in the denominator you add all the impedances that the voltage is across. You add those in series, so you add them together. Okay, so we end up with 2S, S plus 1 times S plus 3, which is exactly what we got up here in the previous one. Alright, so that means we did both of those correct. and then what we'll do is we'll want to decompose that partial fraction. Kind of go through that pretty quickly because we've gotten some practice on that. You plug in values equal to the zeros of those factors in the denominator. Alright, and now that we've found those coefficients, we know that V out in the S domain is equal to negative 1 over S plus 1 plus 3 over S plus 3. Negative 1 being A, 3 being B, and then they're obviously over their respective factors. And then little v out of t is simply the inverse Laplace transform of that. And then you use your Laplace transform table. And that one's a relatively straightforward one. And that's in volts. E to the negative, or negative e to the negative t plus 3 e to the negative 3t. Alright, so essentially it's that. You get a circuit that'll have R, L, and C components in it, as well as a voltage source or a current source, or maybe both. And those voltage and current sources are usually time varying. And then what you'll do, if they weren't time varying, then the analysis would be really straightforward, because the inductor would look like a short circuit and the capacitor like an open circuit. But because the input is time varying, then you have to analyze the circuit as a transient circuit. So then what we do is we convert each component to the S-domain. We model it with the S-domain model for resistors, inductors, and capacitors, and that is an impedance. And then for voltage and current sources, we simply take that signal that's being used as the input and convert it into the S-domain with a Laplace transform. Once you have everything in the Laplace domain, we do circuit analysis in the same way we've done in the past for DC circuits. Once you find an S-domain model for the variable you're looking for, then you do the inverse Laplace transform to get that value or signal in the time domain. So obviously there's some pretty complex circuits that you can get into. This is an introduction to circuit analysis using Laplace transforms. Definitely recommend you do some more examples in the book and in the problems at the back of the book too. Thank you very much.